Chłopaki, the floor is yours.
Thank you. Hello everyone, my name is K.Jankowski, and today together with M.Grotkowski, M.Janik and A.Hanke, it's our great pleasure to give a talk about state-of-the-art techniques in information retrieval and question answering systems. This project wouldn't have been possible with our teammates. We would like to also thank our mentors, Łukasz Treszczotko and Marcin Morzejko, and we would also like to thank TCL Research Europe for supporting the GPU cluster for our experiments. All right, we've got a lot to cover today. We're gonna start with an introduction, tell you something more about information retrieval. We're gonna cover lots of different retrievers, dense lexical, hybrid retrievers. We're gonna show you some very cool models, followed by re-ranking techniques, starting with the simple ones to the more advanced and novel hybrid ones. We're gonna also focus on evaluation and metrics, show you lots of cool results, and end with tips and tricks. All right, so we're gonna start with the motivation. So large language models have taken our world recently by storm, transforming how we work and what we use in our daily life. So our main goal is to further improve their functionalities and turn them into even better personal assistants to help us in our daily lives. If you've worked with large language models, you might have seen that they have some problems. For example, they hallucinate, meaning that the answer that they generate might look okay, but it's actually totally wrong. They struggle with factual knowledge. The update is hard and costly, and even with longer window context and current research, it's still expensive. And what we really would like to have is the functionality where we have thousands of documents, and very quickly we can answer questions to supercharge our business with AI. So in the classical pipeline, when we have a large language model, we start with a question and we rely only on the parametric memory of the model, meaning that all the knowledge is encapsulated in the weights of the model. So if you ask a question and the model was trained on the old data, the answer might not be correct and it's hard to update the model. So in an improved scenario, we have a second model called retriever, and when we ask a question, we do not rely only on the parametric memory of the model, but we rely on the non-parametric memory of an external knowledge database, which consists of documents. It can be Wikipedia. Usually these documents are divided into smaller passages, like 100-word pieces. And here the workflow looks like that we ask a question, retriever retrieves the information needed to answer the question, and then constructs the answer on the sources, meaning that it's more factually correct and easier to update. All right, so we covered the pipeline, and now we're gonna tell you how these retrievers work.
Okay, so I'm gonna talk a little about how those retrievers work, just like Krzysztof said. Given potentially thousands or tens of thousands of documents we want to query, how can we do it efficiently? One answer for that, pretty trendy one right now, is just throw a neural net at it. So dense retriever does exactly that. It represents both queries and documents as vectors. So we have a special model called an encoder. This is usually a transformer that accepts a query or question. It turns it into a vector, and it compares it to other vector representations of documents we want to query. Okay, so how do we achieve that? How do we train such a model? The example above is like a perfect scenario of how such a retriever should work. So we have a query, we present it as some vector, and we have two documents, right? One that answers our question correctly, is relevant to our question, and one that answers it incorrectly. So the one that answers it correctly should actually give us a high positive score in dot product or cosine similarity, and the one that is irrelevant should give us a low score. And in order to do that, we use contrastive learning with a special loss that basically pushes those vectors representations of question and document that is relevant to the question closer, giving us a higher high constraint similarity score, and those that are negative, that are irrelevant to our question, it pushes them apart. And how do we determine if document is relevant to the question? This can be labeled, or this can be distilled from other models that already know this data, and we can use their scores to basically check if a question is relevant to a document. So this is the training procedure of dense retrievers. And okay, so now we have a model. How do we perform inference on it? How do we query it efficiently? So the answer to that is basically documents are large, so we would like to split them into some passages, basically they can be 100-word passages, something small, something containing relevant information. We encode it using our model, and we store it in some vector database, right? We don't want to compute those vectors of our corpus, which is static. We don't want to compute them on the fly. We want to pre-compute them, and then when we have a query, when it's time to ask our model which passages are relevant to our question, we just encode this query and we look for closest vectors. All right, so that was dense retrieval. It's really good at some semantic information, at checking information on average, but in more specialized cases, like words that occur really rarely in our data, we'd like to use something more specific called lexical retrieval. This is your statistical model. It's basically just computes whether some words in our question occur in the document that we are interested in, right? It actually is a bit more complicated than that. It uses something called term frequency and inverse document frequency. So term frequency, again, it just checks if in a document that we are looking at, some words occur. And inverse document frequency boosts the scores of some words that occur very rarely in entire data set. So term frequency is basically based on a single document that we are looking at, and inverse document frequency is a global statistic. It checks if the if the word is occurring very rarely in our data set, just as we can see in this example with amyloid arthropathy. So if a document would contain this word, it means it's probably really relevant to our question. Okay, so some examples of real-world dense and sparse retrievers. So we have Dragon. This is a model from Meta. As I said earlier, it uses distilled knowledge from other models, multiple models, to basically check if some document is relevant to the question or not, and uses that to train the data, to train the model. And as well, we have Arctic Embed. This is a really recent model that uses a lot of new tricks to gain a lot of performance. And in practice, so this BM25 is a lexical retriever, and it can be easy and fast to compute if you choose the proper implementation. So we found out the hard way. So we used the first BM25 Python package you can find, and it worked okay, but it computed really for a really long time. When we switched to implementation in Elasticsearch, which uses a lot of more tricks, like splitting question into more sophisticated tokens and not words, it improved our times by 100 times. So implementation matters. All right. So now Antek is going to talk a little bit about how to actually evaluate those retrievers.
Thank you. Yes, so we would like to see whether our retrievers perform well or not. And thankfully for us, there have been a lot of studies in that field. And basically, what we use is a huge benchmarking data set called BEER. It consists of multiple data sets of various difficulties, various themes. As we can see here, some of the questions are quite easy, like why is creativity important? But also some of the data sets consist of questions which are quite hard and heavily scientific, like what is inverse RL? Another thing that we need to keep in mind when evaluating our models on this benchmark is that there are a few data sets which are sort of outliers. One of the data sets, for example, is fully in German, and this might be important for some models which were not trained on German data. Another data set depends on retrieving the opposite of the query that is being asked, and also some of the data sets have a lot of relevant passages to each question. And now that we know our benchmarking set, we would also want to know the metrics that we use to evaluate our models. And basically, there are four main metrics that people use to evaluate the retrieval task. Two of them are quite basic and probably known to most of the people, the precision and recall. Precision is how many retrieved passages are correct. Recall is how many correct passages are retrieved. Those two are very easy to understand, but they have a few crucial drawbacks. First of all, they do not prioritize or give a better score to a model which retrieves as number one the most relevant passage. And also they quite heavily depend on the whole data set, whether it has a lot of relevant passages per answer or only a few. That's why people came up with two different metrics, mean average precision and NDCG. NDCG stands for normalized discounted cumulative gains. And those two metrics actually fix those issues. They give higher score if your retrieved documents are ranked from at the very top. And also their score is always normalized between 0 and 1, no matter the data set. And let me go over the calculation for the NDCG metric. This is the most widely used metric, and this is what we will actually evaluate in a few moments. So this NDCG, the formula might look quite complicated, but in practice it's not that complicated. First of all, let's look at the case where we retrieve 5 passages, and there's only 3 relevant passages to a given query. So in the first row with the example, we can see what happens if we have the best possible retriever, which retrieves the relevant passages at number 1, 2, and 3. We can see that first we calculate the discounted cumulative gains. This is just a series of fractions, with the numerator being 1 if we have the relevant passage at this place, being 0 if we don't have a relevant passage in that place, and that the denominator is getting lower and lower with each place that we go on to. And what happens in the ideal case is that the score we get as the discounted cumulative gains is, let's say, 2.13. The normalized, that's why the n stands here for, the normalized one is always divided by the ideal one. So in the ideal case, we always get 1. If we, say, retrieve the 3 correct passages but in the wrong places, we get around 0.6 something. And if we retrieve 0 relevant passages, then we get a score of 0. And now that we know what metrics we use and the data set, let us start with some of the first results. So here on this slide, we compared the results of all the baseline models that we used, the ones that were mentioned before. And let me just quickly tell you about what things are in this chart. First of all, we always use the NDCG at 10. So we retrieve 10 documents, and we calculate the normalized discounted cumulative gains. Here on the left, we can see all the different data sets that are being used. And on the right, we have the average over all the data sets. And on this slide, we can see that the dense retrievers like Dragon and Arctic perform overall better than the BM25 ones. However, one of the, let's say, outlier sets, the German one, we can see that actually there the Elasticsearch BM25 performs a lot better than the dense ones. And this is something to keep in mind, because if the dense retrievers were not trained on German data, then they might not understand whatever is coming their way. However, the BM25 is a language invariant. It just looks at the word occurrences, and therefore the German part is not hard for it. So in summary, some of the retrievers capture the semantic meaning of the query, However, other retrievers, due to their keyword search, might perform better at some other tasks. So our initial thoughts were to maybe combine those two retrievers or those two retrieving paradigms. And therefore, in the next slides, we will talk about how we can combine those, how we can use some other methods to maybe improve our scores. And that's what my friend will be talking about right now.
Okay, so a very common approach to further improve the results of the retrieval process is the so-called two-stage retrieval. So in the first stage, we search for the documents from a very large corpus of documents. And then at the later stage, we perform a re-ranking, possibly using a more sophisticated, a bigger model. That will further improve the ordering of our retrieved passages. And it's worth mentioning that during the first stage, we can retrieve more documents than we actually need, so that after the re-ranking process, we can filter the irrelevant documents out. So one of the model class that performs really well for this problem are the cross-encoder re-rankers. And on the contrary to the bioencoders, which encode the query and the documents separately into dense vector embeddings, the cross-encoders take both the query and the document as an input and pass them to a single transformer model, and they generate a relevance score. And in this way, they achieve much better performance than the embedding models at the cost of a higher time consumption, because unfortunately we are not able to pre-compute the embeddings of the passages as we used to. And in our experiments, we used a BGE re-ranker, which is an open source model that achieves very good results.
Yes, and now going to the scores of this approach, we can actually see what we have on the slide is a comparison of the baseline model. And with each step, we just increase the number of articles that this model retrieves, and we just re-rank them using this BGE re-ranker. And what we can see in the case of BM25 is that the more articles being retrieved and re-ranked using BGE, the better the score overall. And this is very consistent. The best results are when we retrieve 80 documents and we let BGE re-ranker do all of the re-ranking down to the 10 we need. A similar story holds when we look at the elastic BM25, which is a very similar approach. Also, the more we retrieve, the better. We let the re-ranker do all the work. The best results are when we retrieve 80 documents and re-rank. However, the story changes slightly when we look at the dense retrievers like Dragon or Arctic. So here, for example, when we look at the Dragon retriever, at some point it is not worth retrieving more articles. Namely, at around 40 retrieved articles, we are getting the maximal score on average. And this might be due to the fact that when we retrieve a lot of different articles, then this BGE re-ranker might introduce some noise by actually pulling some very irrelevant articles to the top sometimes. And an even more profound case is happening when we look at the Arctic retriever, which is in itself quite strong already. At some point when you retrieve more than 20 articles and we use the BGE re-ranker, it actually slightly lowers the scores of the Arctic retriever.
Of course, we cannot talk about NLP without mentioning large language models, and apparently large language models works also for the task of re-ranking passages. And there are many possible ways of how can we prompt these models to actually perform this task. But one of the most commonly used and also performing the best is a so-called permutation generation. And in this method, we prompt the model with a query and also the content of passages, multiple passages, along with some IDs. And then we ask the model to rank these passages based on relevance to the query. And the model outputs IDs in the correct ranking. And in our experiments, we used the rank Zephyr. It's a large language model that is open source, and it was fine-tuned for the problem of re-ranking. And we can see that this prompt of this model that is used, and it uses the method that we mentioned. It passes the query, passages, and outputs IDs ranked.
Yes, and now let's see whether this LLM re-ranker, rank Zephyr, performs better than this BGE re-ranker. So, for example, when we look on this slide, we compare the baseline Dragon and those two re-rankers we mentioned previously. And what we can see on the average scores is that, well, the rank Zephyr re-ranker does not improve over the BGE re-ranker that much, or actually they are very similar in score. However, what we can actually notice is that on the very scientific data sets, all the boxes labeled number 2, the LLM re-ranker, so the green bar, is actually performing a lot better or consistently better than the BGE re-ranker. So it might be the case that there is some semantic knowledge in this LLM re-ranker that is actually useful in that case. And a very similar fact holds for the Arctic retriever, where we can see that on average both of the retrievers, both of the re-rankers actually give the same score. However, on the scientific data sets, the green bar, which is the rank Zephyr, performs the best.
Okay, so we used re-rankers to re-rank the outputs of a single retriever, but it's also possible to use the re-ranker as a way of merging many different documents from different retrievers. And in our experiments, we used the re-ranker to merge the results from a dense retriever and from a classical one.
Yes, and now we can see on this slide we compare, well, we look both at the Dragon and Arctic retrievers. However, the bars on the left are just the Dragon or Arctic retriever itself. However, the bars on the even positions are an ensemble of these dense and sparse retrievers. And what we can actually see is that both in the case of Dragon and Arctic, when we add on the BM25 sparse retriever, we actually improve the results. So the best result we can achieve is by using an ensemble of Arctic, which retrieves 15 passages, and BM25, which retrieves 5 passages, and then we use LLM Zephyr to re-rank them. And what is very interesting to see is, for example, in the data sets where we have seen that the sparse retrievers perform a lot better, this actually we can see in the data that it improves our results vastly.
To sum up, we have two distinct classes of re-rankers, one being the cross encoders that takes only a part of the question and the document, and they achieve a very good performance actually, with having a relatively low latency. But on the other hand, we have LLM re-rankers, which are much slower, but can take many documents at a single inference, and therefore they sometimes perform better. And we have seen that, especially on the scientific domains, they outperform the cross-encoder re-rankers. Now, Krzysztof will talk about how we can combine re-rankers.
All right, so we saw that different re-rankers have different good sides and bad sides. So right now we're gonna combine them and try to get the best out of both worlds. So as Michał mentioned, the cross re-rankers, the M.Janik re-rankers are faster. So we're gonna use that in order to filter out the passages. So we will be able to retrieve more passages and then keep only the best passages. And regarding the LLM re-ranking, rank Zephyr, we'll be able to use it to merge the results from different retrievers and use it. All right, so we're gonna start with the first component we would like to call the chain re-ranking. So the idea is simple. We start with a retriever and retrieve passages. This works with any numbers, but I'm gonna work on this concrete example. So for example, you can retrieve 40 passages. This can come from the first re-ranker, which in our case is the embedding re-ranker, to get top 20 passages, which are filtered out. Further by the second re-ranker being the LLM re-ranker to finally get top 10 passages. As we can see here with our results, we are gonna compare the dragon in green, in blue, with dragon after LLM re-ranking, and later with dragon with M.Janik re-ranking, where we start with 40 passages and end with 10, and the last one is our chain re-ranking. And as you can see, it performs better than both re-rankers used separately. So we can see that we're actually able to get the best out of two words. So we've got similar conclusions with the Arctic retriever. Arctic is a more powerful retriever, therefore the increase isn't that noticeable, but still on some data sets it's bigger. And now we are going to introduce another concept, which we call the split re-ranking. We actually created it in order to solve a problem, because where you retrieve more passages and filter it out to a smaller number of passages, it's not that straightforward, because of course you can promote passages that are initially further, but also you can downgrade the passages that were already very good. Therefore, we introduced split re-ranking, where we take passages, in this case, let's say it's 40, and we keep top 10 passages unchanged, because we hypothesize that they are the best, and we only re-rank the remaining 30 passages, which are re-ranked through the BGE re-ranker to filter them to top 10, and later this gets concatenated. If you would like to further decrease it, we would use the LLM re-ranker. So as you can see here, we compare both Dragon and Arctic, our previous approach, the chain re-ranker that you already saw, with our split re-ranker. In case of Dragon, we unfortunately see a slight decrease in performance, but with Arctic we see an improvement. Also, we are talking about the mean here. The individual data sets differ more. All right, so as we previously discussed the ensemble of retrievers, now we can use an ensemble of re-rankers. So in this case, if we would like to start with an ensemble of retrievers, we would need to somehow combine them into a single output. Therefore, I will be also here operating on this example. We usually want to have an ensemble of dense and a classical retriever, a sparse one. So we start with a dense retriever, retrieve more passages than wanted, for example, 40. We split it in order not to introduce that much noise. So we won't be re-ranking the top 10. We only re-rank the last 30 passages in order to filter them out to top 6 passages, which is later concatenated, so we get 16 passages here. And regarding the classical retriever, we do not split it and just filter it to top 4 passages using the BGE re-ranker, and later it all goes through the LLM re-ranker to get to top 10 passages, and we get an example of retrievers and an ensemble of re-rankers.
Wow, that was quite a model there. But let me go through the results. And here on this slide, actually, don't worry about those different colors and different bars. We go through each of the single building blocks in order, and we can see that adding each of them on actually improves the results on average. So on the left, where we start with just the BM25 retriever, it performs the worst. Then we look at how it performs with the inclusion of the BGE re-ranker. It already improves quite drastically, but it's still worse than the green bar, which is just the Arctic retriever. However, when we use the chain re-ranking approach on Arctic, the red bar, it improves slightly. When we use the split chain, where we reduce the noise because we keep the top 10 of the Arctic retrieved articles on top, it performs even better. But the thing that you saw on the slide before, the brown bar at the very right, it actually gains the best results out of all the combinations we tried. it improves on the average, and we can see that actually on 11 of the 16 data sets in the whole benchmarking set, we beat the Arctic Retriever, which is actually one of the state-of-the-art current open source models. So in summary, when we use the embedding re-ranker, we can filter passages and keep only the best. The LLM re-ranker performs very well, but it works, let's say, on 20 retrieved passages. That's why we use it always often at the end of our pipeline. The split re-rankers reduce noise because we just keep the top 10 of the very strong dense retrievers, and the chain re-rankers can combine different parts of our pipeline.
All right, so we are slowly getting to the end. We would like to, as promised, give you some tips and tricks that we discovered through this project. So these are some engineering tips. So our project was created using Hugging Face, PyTorch, FICE, and DSPY libraries, which we recommend to you. So first of all, we started with the Llama Index library, which is currently a very popular library, and we call it a high-level library because in a very few lines of codes you can create your proof of concept. It's, let's say, it's easy, it's fast, but if you would like to have a very non-standard, customized solution tailored to your needs, so it quickly gets very hard to manually tune it to your needs. So if you want to have a very quick proof of concept, it's good, but if you really want to have an incredible solution, then it's too high level. So in all our experiments, we use Hydra configs. So when you see all the components in our pipelines, retrievers, ensembles, everything, so we wrote this in config files, and thanks to this, we do not have a mess. And it's very easy to manage. It's scalable. If you'd like to change a model, it's just one line of code to change. Also, our pipelines are independent. I mean, each blocks are independent on each other. So as one block finishes the execution, we manually free the GPU memory, and thanks to this, we can fit larger batch sizes and also more powerful models. Also, if you look at libraries, it's always a good practice to see if they support multi-threading, as FICE does, because if you use that, you suddenly get incredible performance boost. Also, you need to remember about batching, because some re-rankers do not offer that. And if you use all these tricks, we have a nice success story, because we started with Llama Index, and then we were able to make our implementation 100 times faster. And it still took 3 days, so that's the reason we were able to be here with you. Otherwise, it would have taken a year. All right, so we are getting to the end. So to sum up our presentation, we told you today about retrieval pipelines, how to improve them, what are the good practices. We covered a lot of different re-rankers, ensemble of retrievers, ensemble of re-rankers. If you are curious if we have some next steps plans, we would like to distill our whole complex pipeline into a single model to put it on Hugging Face, so we will be able to use it, so it could be simple. And also we had to manually tune all the components in our pipeline, and it would be better to have an automatic system that does this for us. So, all right, we would like to thank you very much for your attention. If you'd like to connect with us on LinkedIn, we'll be more than happy to do that. We also encourage you to give us feedback and rate our presentation using the QR code. And if you have any questions, we can take them now. We are also available throughout the conference and later. So thank you very much once again.
Thank you, guys. Congratulations for compressing so much information into this short presentation. To be honest, together with Kuba Nowacki, we were very hard pressed to select the presentations which would be presented live here, because there were so many great submissions. I think this track is the hottest by far. We all know why. But don't worry, the other great presentations are available in the VOD format in your panel. So this one will also be recorded. Was recorded. Yeah, so please leave your feedback. You can also do it later when you watch this on your panel. And now let's take a few questions.
Okay, thank you for the presentation. I have had maybe a question. Have you tried like an, I know that you mentioned like an hybrid search that combines, I would say, the, the retriever and large language models, but, sometimes, over the internet, there are, descriptions of the so-called hybrid search that you actually do the vector and like a keyword search. And I have a question. Have you tried, with this, including, in the results also the keyword search, if that actually improves the results?
Yes, okay, thank you for the question. Yeah, so we actually did this. So all our ensembles were a combination of a dense retriever and a sparse retriever, which actually looks at keywords, and that is mostly what it does. And later we had to use re-ranking to merge the results, but yes, thanks to using the keywords, we're able to get the performance boost, especially in the domains where the dense retriever didn't have the data. So for example, the retrievers were trained mostly on Wikipedia or on English corpus. They struggled in German. So keywords were very boosting it. So actually all our ensembles feature this classical best match 25 retriever in the form of Elasticsearch that looks at keywords, and even slightly better.
Hi. First of all, great presentation. Question, have you used only some benchmark databases of passages available there, or also have you created one of some articles, raw texts? And if yes, then have you considered how the algorithm to create the passages and encode them can impact the overall performance of the retrieval?
Okay, thanks for the question. So actually, no, we didn't do that. We mostly focus on the standard benchmark in order to robustly assess the performance. So we didn't focus on our own articles. If you would like to use your own articles, it will also be, of course, available. If you want to split the documents into passages, so there are lots of techniques currently. These benchmarks are usually quite simple because they just divide the documents into around 100 words, small passages. But there had been some research that if you do it more semantically, like each passage encapsulates like a section or a subsection, it will be much better. So if you'd like to create your own data set, you would also need to look at golden passages. So you would have to create your question and a reference passage that contains the correct answer, which might be also quite tedious for you if you'd like to do it manually. Right now, when you have some LLMs, you might try to use them in order to speed the process up, or start with passages and generate some example queries so you could construct it. But we use a standard data set to be really objective.
So I have a question, because recently I've came across a publication on re-ranking the multiple retrieval systems by using, instead of cross-encoders or dense encoders like you've shown, they were using an approach called a reciprocal rank fusion, in which both of the retrieval systems retrieved a lot more results than they normally would have. And then the retriever selected the one that was agreed on by both the retrievers. Did you try this out?
No, unfortunately, we didn't try that out. But it sounds very interesting, and this might work. Actually, we had some experiments. I can tell you the results because when we wrote our code and we had an ensemble of this dense and sparse retriever. So we had to change some lines of code, because if you say you retrieve 40 passages but they come from 2 retrievers, you might get duplicates. So you do not end up with, let's say, 40, but with slightly less. And what we saw is that usually around like 3 or 4 passages would match. But actually, it wasn't such a big amount that, let's say, a dense retriever and a lexical retriever would agree in, I don't know, 90% of the time. No, it was like a small fraction, and it was filtered by our system not to include the duplicates. But the idea is, the idea is very promising. But you need to watch out not to, because they might not agree that often. It's not. In our experience, this wasn't such a very big number.
Yeah, so thank you for questions. Unfortunately, we've run out of time. So if you have any more questions, please take them off stage with our speakers. And let's thank our speakers once again.